All right, section 3-5 is on displacement, velocity, and acceleration. The objective of this section is given the equation for displacement, find an equation for velocity and acceleration. One other term here that we need to describe or use here before we jump into the next example, and it's this term antiderivative, which an antiderivative turns out to be the same as an indefinite integral. If you recall, that's one of the topics, 4 topics of calculus. But an indefinite integral or an antiderivative is defined this way. We say that g of x is an antiderivative of f of x if and only if the following is true. If I take the derivative of g of x, if that gives me f of x. So g of x is an antiderivative of f of x if and only if the following is true. G prime is equal to function f. So in other words, if I'm given the derivative f prime and I want to go backwards to find out what function f must have been to start with, that's an antiderivative that I'm finding. And that's what the next example actually is going to ask us to do here. Let's take a look at the last example here, example 3. Example 3 says the acceleration of a moving object is given by acceleration a of t is equal to 12t minus 5. And it says where a of t is in centimeters per minute, t is in minutes. If the velocity at t equals 1, so they're telling me that v of 1, if the velocity at t equals 1 is equal to 8 centimeters per minute, 8 centimeters per minute when the velocity is equal to 1, or excuse me, when the time is equal to 1, find an equation for v of t, the velocity as a function of t, and use the equation to find the velocity at the instant when t is equal to 3. All right, so in other words, I'm given acceleration and I kind of want to work my way backwards here to find out what the velocity was. So the first step that I need to understand here is that acceleration, remember, is the derivative of velocity. In other words, you're starting with the derivative, and the question is, what does velocity equal? In other words, find the antiderivative. All right, so to do that, I first have to look at this function that I have for acceleration right here. And I'm going to take it term by term. I've got a sum of functions there, but we're going to evaluate that term by term. And I've just got to use the reverse properties that I've learned so far. So I see that I have a constant of 12 out front, so I know that the constant's going to stay out front when I take a derivative. The constant stays. So when I go backwards, the constant must stay in some way. And secondly, I see that I've got this function here, t, that I'm multiplying the constant by. I can think of that as being t to the first power. And so I'm going to use my power rule in reverse. So to use it in reverse, that means that instead of subtracting 1 from the exponent, I have to add 1 to the exponent. So it's going to become t squared. But I also end up having to multiply, when I take the derivative of a power function, I have to multiply by that exponent. Of course, since we're going backwards, instead of multiplying, we're going to divide. So I have to divide or multiply, I guess, by the reciprocal, I guess is how I'll think of that. But I'm going to multiply by 1/2. So again, the reverse of your power rule says you subtract 1 from the exponent and you multiply by the exponent. Here we're going to add 1 to the exponent and divide by the exponent. Reverse operations, or the opposite operations. And then we have this constant here. And again, you can think of this as being t to the 0 power if it helps you think of it that way. So you see that as a constant times your function. Use the same process here. The constant stays out front. We're going to take that t and raise it to the first power. We'll add 1 to the exponent. And then I'm going to multiply by the reciprocal, or actually I'm going to divide by that exponent, but that'll be multiplying by the reciprocal, so I'll divide by 1, which of course doesn't change the problem. Now the one piece here that kind of gets lost is the fact that when I take a derivative, if I take the derivative of a constant, the derivative of that constant becomes 0. So I have to take that into account here, that there could have been some constant added on to the end of this. We'll call it c. that when I took its derivative, it becomes 0, and I lose it in my acceleration equation then. So we'll account for that by putting a plus c at the end. So let's see what we have for our velocity equation then. 12 times 1/2, that's 6t squared minus 5t plus c. That's our general equation here for our velocity function. And we call it a general equation because I still have that c in it. But they told me that when velocity is equal to 1, excuse me, when velocity at time equals 1 is equal to 8. Velocity at t equals 1 is 8. So I can substitute that into this equation and solve for c. That is, v of 1 has to give me 8. Or in other words, when I plug in 1, actually I should put the 8 at the end, I guess. When I plug in 1 into my velocity function, I'll have 6 times 1 squared minus 5 times 1 plus c, and that's supposed to give me a value of 8. So I have 6 minus 5 is 1 plus c is equal to 8, so that means c must be equal to 7. So it must mean that my velocity function, v of t, is equal to, it's 6t squared minus 5t plus the 7, the value of c we just came up with. There is my velocity function. Now the nice thing about this is you can always go back and check your answer when you find a antiderivative. And the way that you do that is by finding the derivative of the function that you just came up with. So the check here that we're going to do is find out what v prime is equal to given this function for v of t. So v prime would be 6 times 2t to the first power minus 5 times 1t to the 0 power plus 0 is the derivative of that constant. Or in other words, you end up with 12t minus 5. And notice that's the original function they gave us. They gave us the acceleration was 12t minus 5, and they want us to find velocity. So it turns out that, in fact, this velocity function would give us that acceleration. And that's the end of this section here.